Hello and welcome back to Arduino for Amateurs. This is episode number 6, Analog Input. As always, my name is Matt Gracie. I'm a hacker from Buffalo, New York, and I'm a member of the BitHaven Hackerspace. What I'm talking about in this episode is how we use analog data sources, analog inputs, as part of our Arduino circuit. In earlier episodes, we talked about how to use a button. Right? A button being a digital input, either it's on or off, 1 or 0, high or low. We push the button, the value changes, we release the button, it changes back. There's 2 possible states. In this case, we're talking about analog inputs. Analog inputs have gradations, right? They have shades of gray. They have a spectrum of values. It's not just 1 or 0 anymore, but it can be significantly more values. Some of which are greater than others, right? We're talking about something less black and white, more gray. Something like a thermometer or a photoresistor or a humidity detector, right? For this particular example, we're going to use a potentiometer. So this is one type of potentiometer. There are other types that you may get in your hardware kit with your Arduino. This is the kind that I'm using in my particular circuit. And what a potentiometer is a variable resistor. You can see here we've got 3 different pins, 1, 2, 3. The outside pins, one of them is a power in and one of them is a ground. So we hook one of these to our 5-volt line, we hook the other one to our ground line, and power flows into the pot and then back out. This middle here, this is our signal pin. So when we turn this big pin here, this big crank, what we're doing is we're adjusting the amount of resistance in the potentiometer. It's a variable resistor. So it can go all the way from almost no resistance at one end of the turn to maximum resistance on the other end of the turn. As the voltage flows through there, as the electricity flows through there, the amount of resistance is reflected on this signal pin. So this is a reading on the value of this knob, where exactly it is on that spectrum from minimum to maximum resistance. Okay? So what this allows us to do is send an array of values, a spectrum of values into our circuit. It's not like a button anymore. It's not where I just push the button to turn it on and push the button to turn it off. Instead, the value could be 0, it could be 100, it could be 500, it could be 900, right? It could be anywhere in there. So we have to deal with this in a different way, right? We have to use those analog input ports that you may remember from the first video, the hardware video, in order to capture the nuances of this signal coming out of our potentiometer. So let me show you the circuit that I'm using here. This may look a little bit familiar. It's essentially a modified version of the buttons circuit that we've been using for the last couple videos here. So at the bottom here, you can see I've got a red wire and a black wire. Those go back over here. The red wire is hooked to the 5-volt line. The black wire is hooked to ground. So that means that this rail here, the red one is powered. The blue one is ground. So we have 5-volt and ground signal available all the way up and down the breadboard here. On the bottom spot here, we have our LED, our blue LED that we've become such good friends with over the last few videos. That is connected to pin 13, which is the same as the built-in LED pin. So signal can go from the board on pin 13 over to here in, this looks like row 20 or row 19 maybe, on the breadboard. The electricity flows through this resistor. And thank you, Alex, in your comments. You said I did not say the value of the resistors. I'm sorry, I didn't realize that I had omitted that. This is a 220 ohm resistor. So if you're trying to build this circuit at home, that's what you want, is a 220. So the current flows through this across the trench via this resistor into our LED, goes through the long leg, the anode, out the short leg, the cathode, back to ground, and then back down here to the black wire and back into the board. The part that I replaced is up here. In the last video, there was a button here. Now I've replaced it with this potentiometer. So as I said, the potentiometer has 3 pins on it. They are in this breadboard. They are plugged into row 8, row 6, and row 4. They're 2 rows apart. And you see here I've got 3 of these jumper wires, 3 of these DuPont wires connected to those 3 rows of tie points. So I've got this red wire is going from our power rail over to this lower pin, this pin on the row 8 side. The black wire, the ground wire, is going from our ground rail here over to the top pin right here on row 4. And then row 6, the signal pin, is connected via this green wire all the way back over to here to analog input A0. Now you probably remember in our last video, our button was connected to pin 2. So pin 2 is a digital input, and we can see that printed right here on the board, digital input. And then PWM, we'll talk about that a little bit in a minute. But that means that this pin can only detect digital values. Is it on? Is it off? That's it. If you have a sound sensor that's a digital sound sensor, it's basically, is the sound above the threshold or below the threshold? There's no measurement of how much signal there is. It's either above or below a threshold. Analog, on the other hand, this can accept those analog values, those shades of gray. So when I turn this potentiometer, what it's going to do is it's going to send a spectrum of signals, an array of signals, not just ones or zeros, but actual discrete values from 0 all the way up to 1023 into analog input A0 here. So let me flip over to the Arduino IDE and you'll see what I'm talking about. Okay, there we go. So this is a little sketch that I wrote. Again, if you want a copy, let me know. I'll post it on GitHub. But the only point of this is to read the values from our potentiometer and output them to the serial monitor. So let me walk through the code real quick. On the top here, we've got 3 variables. First is our sensor pin. Our sensor pin is A0, so we've set that value. The second one is our sensor value. So we need a variable to store that potentiometer setting in as it's coming from the circuit. So we're calling that sensor value. And then map value. So we'll talk about mapping in a couple minutes right after we go through this code the first time. In our setup, all we are doing is we are turning on the serial monitor here. We don't really need this comment. That's just sort of extraneous left over from somewhere else. So we turn on the serial monitor and then we start our loop. So the first thing we do a analog read function. So our sensor value, we read the value, the analog value from sensor pin. Remember, sensor pin is A0. That's where we have our potentiometer's signal pin plugged in. We print to the serial monitor current value, space, and then we print the value of sensor value. And then we delay for half a second. This commented out map stuff, I'll talk about that in just a sec. So all this is doing is reading the value from the potentiometer and then printing it to our serial monitor. So let me upload this to my Uno. Okay, all uploaded. I will open up the serial monitor here. All right, and it's telling me my current value is 352 or 353. Must be right in between those two. So if I turn this all the way to the right, my value goes to 0. So I have 0 resistance, right? There is nothing coming out of that signal pin. But if I turn it counterclockwise, you'll see that my current value is very gradually growing because I'm turning this knob very slowly. So it's going up, up, up every half second or so. And if I turn it all the way to the other extreme, it goes to 1023. So my range of potential values here goes from 0 when it's turned all the way to the right to 1023 turned all the way to the left. I imagine that if I switched my ground and power pins, it would probably go the other way around. It would probably be 0 all the way to the left, 1023 all the way to the right, because the power would be going through it in the other direction. Potentiometers are pretty much bidirectional. You can wire those outside pins up whichever way works. Now, what is all this mapping stuff? Mapping allows us to take an analog value or a range and downsample it to a smaller range. So you may remember earlier when we looked at the picture of the board. Let me refresh your memory right here. It says digital PWM. What PWM is pulse width modulation, which means sort of a simulated version of an analog signal. An Arduino is a digital device. It can really only produce a digital signal, but by turning it on and off, think like a strobe light, it can simulate an analog signal, by leaving it on and off for particular lengths of time. Anyway, so a PWM output can have a value between 0 and 255. So what I'm doing in this example is I am mapping the value of sensor value from 0 to 1023, which is the analog value that's coming in from the sensor. I'm downsampling that to a value between 0 and 255. So this is a helpful routine that we can use when we have different spans of numbers, different ranges that we want to adjust to one another. So we're taking a value between 10 and 1023 and adjusting it proportionally, keeping in ratio to a value between 10 and 255. So let me upload this now that I've uncommented those lines. Okay, we'll go to the serial monitor. I'm going to clear it so we can see what's happening here. And you see my current value is 1023, so I've got my maximum value, and my mapped value is 255. Now if I turn my potentiometer here, I turn it down, my mapped value is 230 and my current value is 922. I turn a little further, my current value is about 780, my mapped value is about 194. So you can see it's reducing the mapped value. The ratio is about 4:1, right, between my one range and my other, 0 to 1023 and 0 to 255. So what it's doing is it's automatically adjusting that mapped value. So if I was using this to do something like set the amount of power going to a buzzer or a speaker or some other device that I wanted to adjust along this sort of smooth analog value, that's what this map would do. It would allow me to downsample my potentiometer reading to a smaller range that's more appropriate for the output. Okay, so that is what's happening there. So this technique can be used for any analog input. Like I said, if you want to attach a microphone or a thermometer or a humidity sensor or a photoresistor, anything that can output a range of values as opposed to just the digital ones and zeros will work this way. It'll connect to one of those analog inputs and allow you to sample over time that array of potential results. Now, if I want to pair this with an output, I can do it with my LED here, and this is example code that I'm going to use. So if you go to examples and then analog input, right, you'll see this opens up a sample here. Let me just adjust the size of this window. And this analog input, if we read the comment at the beginning here, demonstrates analog input by reading an analog sensor on analog pin 0, which is what we're plugged into, and turning on and off a light emitting diode, an LED, connected to digital pin 13. There we go. That's what we've got turned on. The amount of time the LED will be on and off depends on the value obtained by analog read. So, and then here's the circuit, which we've already built. I showed you a picture of that at the beginning here. So if we look at the code, we see sensor pin is A0, okay, just like it was in the previous code. LED pin is 13, sensor value is 0. Our setup here, and this is that leftover comment that was in my code, because this is kind of what I hacked apart to make that example. The only thing we're setting up is we're saying that the LED pin is an output. So that is going to be our only output is pin 13, the LED pin for the Arduino. And then our loop, we read the sensor value from the sensor pin using this analog read function. We turn the pin on. We delay for sensor value milliseconds, so between 0 and 1023 milliseconds. Then we turn the pin off. And then we delay again for the same amount of time. So it should flash steadily if I keep the potentiometer in one position, but it should flash more slowly if I turn the resistance counterclockwise, if I turn the pin counterclockwise, or it should flash more quickly if I turn it the other direction and that analog value goes down. So I'm going to upload this to my Arduino. I don't need to turn on the serial monitor because, as you notice, this code has no serial monitor in it. But if I hold this up, you'll see I've got a flashing LED here. And then if I turn the knob, that delay goes up, right? Because I'm turning it counterclockwise, which means that analog input value is going up, so that delay is taking longer. If I turn it all the way, then I've got 1023 milliseconds per flash. If I turn it in the other direction, it'll start speeding up. There you can see I'm getting closer and closer to 0. If I turn it all the way to 0, it'll just kind of strobe a little bit. See, it doesn't even finish flashing. All right, so that's probably at about 100. So this analog input allows us to have sort of a sliding scale of values that we're feeding into our circuit, and then programmatically we can act on those inside the Arduino environment, right? We can use this to set all kinds of stuff. If we wanted to build a circuit that strobes the lights faster when the ambient light goes down, we could do that with a photoresistor. If we wanted something that activates a circuit when soil humidity reaches a certain level, we can do that with a humidity sensor, right? There's a lot of these analog inputs that we can use with the Arduino. And now we know how to do it. You just hook it up to one of the analog input pins, account for it programmatically in the Arduino here, and then write your program to generate the code and the outputs that you want. All right. I hope this was useful for you. I always think that the difference between digital and analog stuff is fascinating. That's one of the cool things about the Arduino is it lets us kind of play in both places at the same time, writing this digital code, but interacting with the ambiguity of the analog real world while we do it. All right. Thanks a lot. I'll see you in the next video.